Hi everybody. The purpose of this video is to review the design space of data structures in terms of these various design dimensions, and then to talk a bit about the basic building blocks of data abstraction. So in reviewing data structures, perhaps the most basic design dimension is the physical arrangement in terms of linear versus nonlinear. So a linear data structure would be, for example, a list or a queue or a stack. In all those cases, the conceptual physical arrangement is linear. There is a clear positional order, and you can traverse these data structures in a linear kind of order. Nonlinear data structures, examples would be trees, graphs, and the like. And there's an overview here. So let's zoom in a bit. And this elaborates a bit more on this design dimension, where the linearity is really not so much about the arrangement in memory at the physical level, but more at the logical level. So a linked list is considered a linear structure even though the nodes might not be in consecutive order in memory. So in any case, there are other data structures such as sets or maps that fall along a different dimension because they could be implemented in terms of linear or nonlinear data structures. And that brings us to the next design dimension, which is position-based versus policy-based. So a good example of a position-based data structure is the list, because you have random access to items at particular positions, where the key element is really less the random access, but the fact that there's a meaning to the position of an item in the structure. So for example, in a list I can say, well, this item is the third item in the list, whereas in a set I cannot do that unless perhaps the set is ordered. And a policy-based structure would be one where there's some kind of policy that determines in which order, for example, you see the items, or where the data structure decides based on the policy where it is going to put an item that you insert. So again, the position versus policy. When you insert an item into a list, you can say, well, I want this item to go after the third item, so it then becomes the fourth item, even though there might be other items that then get shifted to make room for the new item that you're inserting. Whereas when you're inserting an item in, let's say, a set, you just tell it, well, I want to add this item to the set, and then the set decides based on some internal policy where it's going to put the item. And a good example would be the binary search tree implementation of a set, where in fact that would be specifically of an ordered set, although you don't need to worry about the ordering unless you need it. That's tied to our fourth point here. But let's say you insert an item in a set that's implemented as a binary search tree. You just tell it, well, I want to insert this item, and then it decides where exactly to put the item. Okay, so a hash table is also policy-based, where the policy would be the hash function. You just tell the hash table, I want to insert this record, and the hash table would then look at the key of the record, apply the hash function to that, and then decide where to put that record in the hash table. So that's another example of a policy. And there is a design document for the collection classes in the GCC library. So this explains it a little bit. So for example here, map and set semantics, how they relate, and there's an introduction here. Also elaborating a bit on the hash example and the set example and how set relates to map as a special case. All right. Now back here, as we've seen in recent discussions, data structures have performance characteristics, and in some cases you have different implementation choices and they perform differently depending on the kinds of operations that you perform. And if we look here at the recent project, what we see here is a fixture which is any kind of linear structure that would implement the buffer interface. So that part is not explicit here. And as we know, there's in Scala, there is the list buffer implementation, which is linked list based, and the array buffer implementation. And these correspond to linked list and array list in the Java collection classes. So they're the pretty much drop-in replacements for those Java collections in Scala. Okay, and what we're doing here is in the first little experiment here, we're doing a whole bunch of random accesses to items at specific positions in the data structure, although these random accesses in fact happen to go from front to back. Okay, but that's really not relevant here because we're doing each access as a separate random access. And what you would have seen here is that the performance differs between list buffer and array buffer. And in the second timing experiment, we're doing insertions and removals at the beginning. And as you know, a linked list supports just plugging in a new node into the existing structure for implementing this operation, and an array list requires you to make room for the new item. Okay. Similarly, if you remove an item from a linked list, you just kind of untie that node that contains the item. So that's pretty simple if you're already looking at that node, whereas in an array list, you have to basically shift the items that come after the item you're deleting so that the item that you're deleting, that spot isn't empty, so that you rearrange the items again in contiguous order. Okay, so there are these performance consequences of your implementation choices. And this ties also to the last item here in the design space, which is how do you tie data structure choices to requirements? So one is actually about the functional requirements. So in some cases, the functional requirements, such as, let's say, a set that also has an order to the items, as opposed to an unordered set, will require you to choose a particular implementation. So this is actually tied to the example down here and the link here, which is this one from the Java collections tutorial. Okay. So when you look at set, okay, that is a common interface that the implementations hash set and tree set share. So what's the difference? Well, there are differences again in terms of functional requirements and in terms of the non-functional performance requirement. What can a hash set not do that a tree set can do? Well, a hash set cannot give you an ordered set. So if your functional requirement is an ordered set where if you visit the items in the set, you want them to be in some kind of order. For example, if they're strings, you want to visit them in lexicographic or alphabetical order. Or if they're numbers, you want them in ascending numeric order. Then you would have to choose a tree set to meet that functional requirement as opposed to a hash set. Okay. So that's a situation where your functional requirements determine your implementation choice. The other situation is where your non-functional performance requirements determine implementation choice. So just like we saw in our example project, that if you want, for example, direct access to any item to be fast, you have to choose one kind of list implementation. But if you want insertions and removals to be fast, you might have to choose the other one. Just like that, in the case of sets, you make this trade-off here. So a hash set, if it's not very full, can perform in close to order 1 for lookups. But when it gets full, the performance degrades and the different buckets in the hash set will degenerate to linked lists. So if you have a very full hash table and you're looking up an item and you're unlucky and the hash function sends you to a bucket with a long list of items that are there because of collisions, then looking up the item in the hash set degenerates to a linear search. So it's no better than a linked list or in terms of performance. So the lookup degenerates to or degrades to order n when you would have preferred order 1. Whereas a tree set will consistently give you order log n performance as long as you're using a decent tree set implementation based on a decent binary search tree implementation that rebalances itself from time to time to avoid the tree set or the binary search tree from degrading also to a linked list. So if you have a regular naive binary search tree implementation, and let's say you insert the items in ascending numeric order, then you basically have a linked list that is descending down to the right. So in other words, the tree degenerates to a linked list, and then lookup will also degrade to order n complexity as opposed to order log n, but they're good, widely known balancing binary search tree implementations, and any decent tree set implementation would use that kind of an implementation. So you would consistently get order log n. So again, that's a decision that will depend on what you require. So if you cannot predict the extent to which your hash table might get loaded up, you might be better off with a tree set implementation where at least you have consistent order log n as opposed to situations where you might degrade to order n, and then you might notice a performance lag in the interaction with your application. So a lot of these things depend. In some cases, they cannot be predicted easily, and they will depend on experimentation. And that's why, in general, it's important to have a running system early on so that you can experiment early on and then make these kinds of decisions. And you can also revisit earlier decisions if you architect your system in a reasonably modular way so that you can easily plug out the less performant implementation and plug in another one. Kind of like here, except we would have to perhaps make the interface explicit here, the fact that it's a buffer, and we could plug in either implementation of buffer. Okay, coming back now to these data abstraction topics. So this is really a more basic discussion of how do you arrange data. Let's say if you have things like collections, anything that goes beyond just scalar data. If we didn't have these kinds of building blocks, we would have a hard time, for example, writing a program to as simple as adding up a list of numbers, because we wouldn't be able to express the list. So we would have to have somehow each number in a separate variable, and then add up these variables explicitly, as opposed to having a loop. Now you might say, well, as long as the numbers are in a file, then I don't need a collection in the program, because the file serves as the place where we're storing the items. And you could just say, well, for each item that I read from the file, I can just add it to a sum that I keep, a current running total. And that's true, then I don't need a list in the program. And in fact, these are good implementations, as we discussed in an earlier project, because they scale to arbitrary sizes of input. So generally, it's a good idea to avoid storing collections in memory, although that trend is also shifting, because if you have to perform a lot of crunching, now with memory getting cheaper and cheaper, there is actually a trend toward doing more things in memory involving larger data structures. So that's something that the big data analytics community is doing. Okay, but conventionally, let's say, assuming that memory is a limited resource, you're usually best off to load in memory only those things you need to operate on quickly, so that they won't become a performance bottleneck. In any case, so it's beneficial usually to have a way to describe collections of items in a uniform, systematic way, as opposed to just having individual scalar variables that I cannot loop over. Okay, so that means we need some way to aggregate, and aggregation is actually a little more basic and general than forming a collection. Okay, and aggregation can be as general as just saying, well, I want to combine pieces of different types. Okay, so for example, if I want a node that has a field for a data value, and then to be able to use that node to build a linked list, I also have to have another field that is a pointer or reference to some other node. So in a sense, that node type is recursive, because it has that reference to something like itself. And then you can create a bunch of those nodes and then connect them to each other, because each node's next reference can refer to another node, and there you can build the linked list. So formally speaking, these are also called product types, and they're known in different languages either as structs or records. And in an object-oriented language, you can think about a product type as an object without methods and just public instance variables. So those two mechanisms together, addressing and aggregation, will basically allow you to build arbitrarily complex data structures. Okay? Well, so how would you build a tree? So how's a node in a tree different from a node in a list? So if you think about that, then the answer will pop out. Will pop out. Okay. So anyway, now another data abstraction mechanism is variations, and you might have seen in object-oriented examples that you might have a common abstraction such as shape, and then you might have specific shape classes such as circle, rectangle, and so on. So that's an example of variation, and conceptually speaking, those are called sum types, where it's basically a tagged union. Whereas product is like a Cartesian product, where you have to have an instance of the product type, you need to have components of all the constituent types present. So for a node in a linked list, which is a product, an instance of a product type, you have to have a data value and the reference to the next node. Whereas in a variant, in a sum type, you have one kind of shape, even though, either a rectangle or a circle, even though both of these are part of the same sum type. So they both implement that common abstract shape interface. Okay, so let's briefly discuss an example of a mutable set abstraction. And the common abstraction here would be the set interface that says, well, we can add elements, we can remove elements, we can check whether an element is present, we can check if the set is empty, and we can ask it how many elements it contains. And that would be this common abstract interface, a common abstraction. And now we can have several possible implementations. And we already had a little bit of this discussion just a little while ago. So we could have a binary search tree implementation, or we can have a hash table implementation. And then there's another interesting set implementation called a bit vector, which is very efficient and uses very little space, but it works really only for small underlying domains. And bit vectors are actually used widely in system programming. So for example, your file system permissions are usually expressed as a 4-bit bit vector in Unix, and the most familiar bits are the the last three, which refer to read, write, and execute. Okay, so each bit determines whether the permission is present or not present. Okay, and you don't need a heavyweight search tree based set to express this, because you know that you only have these 3 or 4 permission values. So all you need is really a 3 or 4 bit number, meaning even half of a byte in memory, and you just set the bits corresponding to these permission values. So each bit is like a little on-off switch that says whether or not the permission is there. Okay, so bit vector is really efficient in that sense, and the limitation then is it works only if your value domain is sufficiently small so that it can be expressed as a relatively small number of bits. Typically what people use is up to, let's say, 32 such bits, or 64, corresponding to the size of an int or a long int, that are actually represented as a scalar value in memory. So in other words, we're mapping a set onto a scalar numeric value onto each bit in such an integer value. Okay, well, so those are all good, reasonable set implementations: binary search tree, hash table, and bit vector. And in practice, you would use, in application programming, you would probably use the bit vector less. You'd usually choose binary search tree or hash table based on, as I just mentioned earlier, the functional requirement, whether or not you need ordering, or the non-functional performance requirements, whether you need predictable performance, or whether you were assuming that the load remains low and you go for the potentially faster performance of a hash table. And then you could also implement a set as an array or a linked list, where the problem is you have to look at how well it supports the operations required by the abstraction. So adding and removing elements might work okay, but checking whether an element is present in any kind of linear list is an order n operation. So here we have a problem if we do a lot of those kinds of lookups. Okay, so that's why in general those kinds of implementations are considered much less reasonable. And again, the tutorial here, the Oracle Java collections tutorial, basically shows again, that you have these collection interfaces, and then based on this combination of functional and non-functional requirements, you pick one of the available implementations. So for list, you choose between array list and linked list. For set, you choose between hash and tree set, and map is this kind of generalization of set where you map a key to a value, whereas in a set you could say, well, it's like a map where you don't care about the values, you care only about the keys. And you make that choice based on the combination of requirements. Very good. So this is really just intended to summarize some of the topics that you've already experienced through some of the project assignments. Okay, that's it for now. Please stay tuned and talk to you soon.